So let's talk first about the capacity of a system. The bit rate of a system increases with an increase in the number of signal levels that we use to denote a symbol. We've discussed this many times with the letter M. As we increase the number of levels, we can have an increase in the bit rate. A symbol can consist of a single bit or k bits, and the number of signal levels, as we've mentioned, is M, and that equals 2 to the kth power. As the number of levels goes up, the spacing between the levels decreases if we have a fixed supply. Because of this, the probability of error increases, and also noise causes a problem. So now let's talk about the Nyquist theorem. And one of the confusing parts that may be for this lecture for you is that you've learned about Nyquist sampling in signal processing, and it's going to seem like what we're doing is actually in violation of that. So I want to tell you a little bit about Nyquist's theorem with regard to pulses, and then we'll do a couple examples to hopefully help you understand that. So the Nyquist theorem states that for a noiseless channel, the rate at which we can send pulses is equal to twice the bandwidth. So FP is the pulse or the symbol rate, and B is the bandwidth. So think about this. This is saying that if I have a bandwidth of 1 kilohertz, I can transmit pulses at 2 kilobits per second. And if you're wondering how we're going to do that, just remember back to this whole aspect of a Nyquist pulse taking up only half the bandwidth of its period. We're going to go into that more in just a moment. So we can extend this theory if we use M levels, and we can say that the capacity, and the capacity represents the maximum theoretical limit. And so we should interpret that as it can never get higher than that, but likely won't even get to that number. So it tells us the maximum that's possible. And this is equal to 2b times log 2 of m. And that makes sense, right? Because we get a bit for every power of 2 levels of m. And so we can just write that as 2bk. And so our previous example with a 1 kilohertz bandwidth, we could have a 2 kilobits per second. However, if k was 2 or 3, we could increase that even more. So C is our capacity in bits per second. It's sometimes written BPS or B over S. Both are the same. The bandwidth in hertz in B, M as we described before, K is the number of bits. And we can also talk about the spectral efficiency, which is the capacity. I'll say this is the max, because capacity represents the max over the bandwidth. Now, it's interesting the units, because this is bits per second times 1 over hertz, okay? And this is said as, if we're going to speak this out, this is bits per second per hertz. That's how we say it. Now, the reason we say it that way is so you remember its origin. If you look at this, this is a unitless number. And if we notice hertz is actually 1 over seconds, this is bits over seconds over 1 over 1 over seconds, and this just equals bits. So the reason we say per second per hertz is so that we remember that we're actually talking about this ratio here. Okay, now let's get back to this. Makes sense that we can transmit symbols at twice the bandwidth of a system. So let's imagine we have a sine wave that is a period of 2 microseconds, and so its frequency would be 0.5 megahertz, and its bandwidth, we'll say, is 0.5 megahertz. We're talking about a single tone here, but I think we can understand that. If we wanted to sample this from signal processing theory, so we wanted to sample the sine wave and recover what it is, we've all learned that we would need to sample it twice its frequency, or 1 megahertz. And that's still true. We're not saying that that isn't true in any way. And so sampling is twice the bandwidth for the sine. And there are 2 samples per period. And so I just want to draw that real quick. So if I have a sine wave, And this is t. I have a sample here, and I need a sample here. And you can see the repetition rate for my samples is going to be t over 2. And remember that my bandwidth of the signal is 1 over t. And so the bandwidth of my samples is going to be 2 times 1 over t. Just the inverse of that. Okay? Now a Nyquist pulse, let's say it has a period of 1 microsecond. It has a bandwidth of only a half a megahertz. So right off, we start to see that its period and its bandwidth differ by a factor of 2. We would expect a period of t equals 1 microseconds to give us a bandwidth of 1 megahertz. Now think a minute, why is it that it doesn't? Well, the key is that it's a Nyquist pulse, and we know that the bandwidth is 1/2 of the repetition rate. And so we know that the bandwidth is going to be twice what it is for t. So the bandwidth is 1 over t, and so we're going to end up with only half of that is being needed, so 1/2 of t over 2. Sorry, 1/2 of 1 over t. And so the symbol rate is twice the bandwidth for the Nyquist pulse. This is what we've just been talking about. And this has to do with the fact that the Nyquist pulse occupies half the bandwidth of its repetition rate. And the other thing is we only need 1 symbol per sample. So if you go back to old Nyquist of the sine wave, I need 2 samples here. But as we'll see in just a second, I only need 1 for each symbol. So I've drawn here, or actually copied from Wikipedia, the spectral of a Nyquist pulse and also the time domain. So you can imagine for the time domain, it's pretty obvious to see I just need 1 pulse here. And if I came along with another pulse right here at t, I could generate another pulse perfectly fine. And because it's Nyquist, remember I have 0 crossings at integers of t, so I don't have any interference. So I can run a repetition rate at 1 megahertz, right? Because I just need 1 pulse that is there. And so you can see my pulse rate is twice the bandwidth. My bandwidth is 1/2 over t, or 0.5 megahertz. Yet my repetition rate is going to be 1 megahertz. And it all comes from the fact of this half bandwidth, and we only need 1 symbol for the pulse. And so what you need to remember is there's 1 symbol per sample, and the bandwidth is 1/2. And you'll understand where we get this 2b for this. And remember, Nyquist said Fp equals 2b. And the 2 is what we need to understand. All right, so let's do a couple quick examples just so you have down how to calculate this. First one is easy. BPSK in a bandwidth of 5 kilohertz, calculate the maximum bit rate C. Well, this is pretty easy. BPSK is M equals 2. It's binary phase shift key, so C equals 2 times 5 kilohertz times log 2 of 2. And log 2 of 2 is just 1, so this is just going to give us 10 kilohertz. Okay, that's pretty easy. All right, now let's look at a different example of 4 QAM, same bandwidth. Well, M now equals 4, and so C equals 2 times 5 kilohertz log 2 of 4. We know this is equal to 2, and so this is just going to be 20 kilohertz. Okay, pretty simple.